So here we have week 1 homework problem number 2. The diagram is of a roof truss, and as the problem states, the distance from A to D, so this distance from here to here is 18 feet as is given on the diagram, and the distance from D to C, so from here to here, is 36 feet, also as given in the diagram. BD is given as 14 feet, which we show out here. I'm going to go ahead and draw that label in right here so that it's a little bit more visible. And they want to know, what are the lengths of the top chords AB and BC? Well, let's look at AB. We're trying to find this, and I'm just going to label it as length AB. Well, this is pretty straightforward because we know that this is 90 degrees. And essentially in this type of problem, you can assume that things that appear to be vertical are truly vertical, things that appear to be horizontal are truly horizontal, and therefore, unless they give you some statement, if an angle appears to be 90 degrees, it is 90 degrees, which is pretty standard in building construction. So if we were to solve for length AB, well, what does length AB equal? Length AB, we don't know exactly, but we know that length AB squared equals 18 feet squared plus 14 feet squared. Now, plugging and chugging on the calculator, 18 squared is 324, and then we're going to say plus 14 squared. And we're able to do this because of the calculator's understanding of order of operations. So the number that you see here, this 196, that's 14 feet squared. To get the sum of those two answers, which we see the addition problem displayed up here, to get the sum you have to hit the equals key. So 18 squared plus 14 squared equals 520 square feet. So we can come down another line. AB squared equals 520 feet squared. And again, the way you solve this is we just simply take the root of both sides. Well, the root of AB squared is just length AB. The root of 520 is, so if you're using a calculator of this variety, it may or may not have a square root sign, but you have a couple of options. You can take the y-th root of x, or what I think is a lot easier is we just raise the base to the reciprocal of the root we want to take. So the reciprocal of 2 for square root is 1/2. So I'm going to raise it to the 0.5 power. And we find that the length of side AB is about 22.8 feet. Now let's think about if that's reasonable. If we come up here and we diagram this length from here to here, about 22.8 feet. Well, it is the hypotenuse of the triangle, so one of the things we know is that it has to be the longest side. And if we look at the other two sides, it is indeed the longest. The other thing is, it's within reason. You know, if you think about if you laid this whole triangle out flat, in other words, if imagine that you made this angle greater and greater and greater, well, eventually you would get a straight line where it was laid completely flat, where that angle had opened up to 180 degrees. And if we took this triangle and folded it open like this, you'd have 14 feet here, 18 feet here. The longest you could ever get if you folded the triangle completely open until it ceased being a triangle would be 18 plus 14, which would be 32 feet. So what do we know? Well, we know it can't be less than 18. We know it can't be more than 32. And we know, just looking at the diagram, that that number looks about right. Now let's look at the process for top chord BC. So top chord BC, real similar problem, right? It's some number of feet. We know, though, that this angle is 90 degrees. It's the height of the triangle is, again, 14 feet, and the length is given in the problem, 36 feet. So again, no need for trigonometry on this one. All we're going to do is we're going to say that length BC squared equals 14 squared plus 36 squared. And you can start to kind of think about reasonable numbers, you know, like 40 squared is 1600. So when I square 36, I should get something close to but less than 1600. So again, that 14 squared, you'll recall, is 196, plus 36 squared, 1296, so it's less than 1600, but it's in the ballpark. So BC squared equals 1492. So we could write that down here. 1492. And again, square root both sides. Square root of BC squared is just simply length BC. The square root of 1492, I'm going to raise it again to the 1/2 power. And its length is about 38.6 feet. Now let's think about, is that reasonable? Well, again, we know that it certainly cannot be less than 36 feet. And it can't be more than 50 feet, just by basic properties of triangles. So certainly we're in the ballpark with 38.6 feet. Now I'm going to clean this drawing up a little bit, and then we'll prepare to tackle the last part, which is figuring out angles A and C. So here you see the drawing with the dimensions that we've calculated drawn in, as well as those that were given in the problem. You'll note that I've used the squiggly symbol in front of the answers that we arrived at here. You can see the approximately equal to symbol, and that's to acknowledge that some rounding happened in this answer. And that's going to matter because at some point we may have a choice, for instance, between finding angle C by taking the cosine of, and we may set the cosine of angle C equal to the adjacent and the hypotenuse. But remember that that hypotenuse has been rounded, so that we can't be totally confident in the accuracy of that number. A far preferable method would be to take the tangent of angle C and set it equal to 14 and 36, because those were both given as exact numbers. You'll find the same thing over here. You know, a good practice is, if you can ever take an actual measurement into a calculation as opposed to a number that was calculated in a previous step, take the actual measurement. So the last part of the problem is to find angles A and C. So here's angle A, and let's think about what we know about angle A. Well, we know the hypotenuse, but it's a calculated number. However, we know the adjacent side was given as 18 feet, and the opposite side was given as 14 feet. So if we think about what function is appropriate, remember, so, ka, toa. Well, the two numbers we'd like to work with are the opposite and adjacent, because they were given in the problem, and as such we can be more confident in their precision. So, opposite and adjacent, the function that relates them is tangent. So here's what we'll do, is we'll say the tangent of angle A equals the opposite over the adjacent. So the opposite, 14 feet. The adjacent is 18 feet. And you'll notice that both of these measurements are in feet. We're dividing feet by feet, which means the units are going to wash out. And you're just going to get a dimensionless ratio. In fact, let's put that in decimal form, because if we're going to use a trig function chart or the calculator, both of those are going to work in a decimal form. So the way we get the decimal is we take 14 divided by 18. And you can see, and again I'm going to use the approximately equal to, because that's a repeating decimal. We can never be perfectly accurate with it. Approximately equal to 0.7 repeating. So we'll go 3 digits here. 7, 7, and then we're going to round that last digit to 8. So the question you got to ask now is, what number has a tangent, or what angle has a tangent of 0.778? So one way, the old way to find this out, is we would look at a tangent table that you'd find in a book. So this is the tangent table that is, or the trig table that is in your course pack, and you'll notice on the left side is angle measured in degrees, and across the top these columns represent different functions. So we're going to start with the tangent function at 0. We're going to come down this column until we get close to 0.778, and you can see that the number that is closest to this, if we come across, is 38 degrees. That'll get you in the ballpark. An alternative method, if you've got one of these whiz-bang calculators, is we can do an inverse function, and when we click the inverse key, you'll see that now all of the trig functions have a -1 exponent, and so in this case this means the inverse of tangent, or sometimes you'll hear it called arctangent. So if we apply arctangent to this, it'll give us the angle. Again, we're in degrees mode, so it'll give us the angle in degrees associated with that tangent. And you can see that we estimated from the trig table that it was close to 38 degrees, and using the calculator we're a little more precise. We'll call it 37.9 degrees. So what do we know? We know angle A equals 37.9 degrees. Now that's an approximation, so really this should be is approximately equal to that. Certainly good enough to set the miter saw. Maybe not good enough for space flight, but for building construction purposes, 1/10 of a degree is plenty close. So 37.9 degrees for angle A. Angle C, it's the same story. You know all three sides of the triangle. However, the most preferable is to use the tangent function to relate the opposite and adjacent. So if we write this one out, tangent of angle C is equal to 14 over 36. Oops, 36. Again, the units for both of these are feet, so the units wash out. If we pull up our calculator, we will do 14 divided by 36 to get a decimal. Okay, and then we can either look it up or we can use an inverse trig function, and we find that angle C is about equal to 21.3 degrees. And again, this should be is approximately equal to. So angle C is 21.3. Now, the question could be asked, you know, how about the remaining angle, angle B? If we look at it, it looks like it's a little bit more than 90. Well, remember that all triangles have 180 degrees. So if we wanted to find angle B, we don't need to use a trig function anymore because we know the other two angles. We can just simply say that angle B equals 180 minus 37.9 minus 21.3. And if we punch that up on the calculator, we find that angle B is approximately equal to 120.8 degrees, and that does make some sense. Just visualizing the angle, we know it's something more than 90. 120.8 looks reasonable as an angle. So you can see that you can get through this whole problem using Pythagorean theorem and then some basic trigonometric functions.